All right, let's work through this together now. So if you got stuck on this because it was so nasty with the algebra, that's understandable. So again, we're trying to derive the derivative of x to the 1/3, which again, we know by the power rule should be 1/3 x to the negative 2/3, at least if x is non-zero. And I said this limit right there, that's the definition of the derivative written in a little different way than we typically write it. But this picture helps you see that it's equivalent to the other way. It's this limit we want to calculate, which you write initially like this here. And again, it's very unclear unless you got some experience what to do here. So I was telling you what to do. Multiply by this very disguised form of 1. That green pen's going out too. And what happens on the top? If you distribute this through, multiply each term on the right by each term on the left once, what do you get? Well, first, y to the 1/3 times y to the 2/3 is y to the first power. So you just get a y. Then you got y to the 2/3 times negative x to the 1/3. That's a minus x to the 1/3 y to the 2/3. Right, multiplying those two terms right there. Next, multiply this term in the middle on the right by each term. So I have an x to the 1/3 y to the 1/3 times y to the 1/3. That's plus x to the 1/3 y to the 2/3. Hey, look at that. Those two things are going to cancel. How about that? Then multiply it times negative x to the 1/3, get minus x to the 2/3 y to the 1/3. Then go to the last term, x to the 2/3, and multiply it times each term on the left. X to the 2/3 times y to the 1/3 is, well, exactly what I said. And then x to the 2/3 times negative x to the 1/3 is negative x to the first power. Leave the bottom factored. It's just simpler. You're less likely to make a mistake, and you don't need to multiply it out. It's the top you wanted to multiply out because almost as if by magic, a bunch of stuff cancels. This cancels with this, and this cancels with this. Okay, we get a bunch of cancellation. And we're left with just a y minus x on the top. What are we left with on the bottom? Well, we didn't cancel anything yet, right? That's still y minus x times x to the 2/3 plus x to the 1/3 y to the 1/3 plus x to, there's a mistake here. There should be a y. Y to the 2/3 times x to the 1/3 y to the 1/3 plus x to the 2/3. That's a y there. Hey, we got lucky again. The y minus x here divides out with the y minus x there. Not to leave a 0, right? Because you're dividing out, but to leave a 1 instead. This is the limit as y goes to x of 1 over y to the 2/3 plus x to the 1/3, y to the 1/3, plus x to the 2/3. Is this a continuous function of y? Think of x as fixed. Is that a continuous function of y? Well, as long as we don't divide by 0, right? Is it continuous when y equals x? Once again, as long as you don't divide by 0. That'll be fine as long as x itself is not 0, right? Does that make sense? As long as x itself is non-zero, as y approaches x, this thing will be defined. I won't be dividing by 0. So now I can go ahead and plug in y equals x. And look at this. Something kind of magical happens again. That's the same as x to the 2/3. I've got 3 terms that are all x to the 2/3 being added together. That indeed is 1 over 3 times x to the 2/3, just like we got before, if x is non-zero. Okay, so we have verified the power rule in the case where n is 1/3. You might wonder, how in the world do you possibly verify the power rule when n can be anything? We just did it for 1/3 and it was this hard. How in the world would you do it when n is like 47/69 or something like that? Or an irrational number like pi? Well, you need other techniques. This kind of approach doesn't work in the general case. Okay? But we're happy that it worked here. This x to the 1/3 graph is a continuous function. Do you see it there? The graph is continuous everywhere. You can graph it without picking up your writing utensil. But evidently, it fails to have a derivative when x is 0. Why? Doesn't it look like it has a tangent line there? Did we really prove f prime of 0 does not exist? We should probably do that separately, because really in doing these calculations, we were implicitly assuming x is non-zero. What if we did f prime of 0 separately as a separate calculation? Here I'll go ahead and go back to the h notation. Limit as h goes to 0 of f of h, f of 0 plus h, which is f of h, minus f of 0 divided by h. The function is the cube root function. 0 plus h is h. F of h is the cube root of h to the 1/3. F of 0 is 0 to the 1/3. Simplify. This simplifies to h to the 1/3, and then I can subtract exponents. I could write this as h to the negative 2/3, 1 minus 1/3, or I could write it as a little bit more easy to see, 1 over h to the 2/3. And that limit most definitely does not exist, dne. You can't plug in 0. And in fact, if you think about it, if you plug in numbers really close to 0, but not equal to 0, like 0.1 or something, or 0.01 or 0.001, h to the 2/3 is also going to be really close to 0. 1 over a number really close to 0 is very, very large. This limit does not exist because this function of h goes off to infinity as h approaches 0, which does mean f prime of 0 does not exist. What's really going on here with this graph? The tangent line does exist, but it's vertical. It's got an infinite slope, you might say. Technically speaking, we'd say the slope is undefined. So yeah, f of x equals cube root of x, x to the 1/3, is differentiable, has a derivative everywhere except 0. We say this is differentiable. Differentiable means has a derivative. You can differentiate it to get a number for all x except x equals 0. It's continuous at 0, but it fails to be differentiable there. Let's use Mathematica now to try to visualize this even better, perhaps. One thing about Mathematica is that it's programmed by a very top-notch physicist who, well, most physicists and most mathematicians, when they think about cube roots, they're thinking about actually complex numbers. And so, for example, if you type into Mathematica, what is -8 to the 1/3 power? If I recall correctly, I believe it does not give you an answer of -2, even though that is the real answer. The cube root of 8 as a real number is -2, because -2 cubed is -2 times -2 times -2 is -8. But I think this is going to actually give us a complex number, or maybe it just spits back the exact same thing I typed. Almost. If I approximate this, one way to approximate numbers is to do a // and then capital N at the end. // is what's called a postfix operator. We're just doing something at the end. The capital N means numerical approximation. There's what I get. 1 plus 1.73205i. What? Yes, that is the imaginary unit, I. You type it and you have to type it in as a capital I, whose square is -1. Mathematica is being too fancy for our good. It's being fancy enough for higher mathematicians and physicists' good, but a little too fancy for our good. So how do we fix this? It's got a built-in cube root function, which automatically gives the real cube root, -2. Use that instead. You want a real number answer for a cube root in Mathematica, you have to type cube root with a capital C and a capital R of whatever you want to take the cube root of. What's the plot of this function look like? Plot cube root of x, x going from, say, -8 to +8. Well, it's pretty similar to what I drew. And yeah, this is part of your participation, by the way, is having this open and doing this with me. There we go, just like I showed you before, right? On paper. Looks like this. How do we understand the fact that the tangent line at the origin here is vertical? I mean, the graph itself can't possibly be vertical, can it? Because it's got to pass the vertical line test, right? You know that. Graphs of functions have to pass the vertical line test. What's the vertical line test say? Graph of a function, any vertical line cannot do what? Can't intersect it more than once, twice or 3 times or 4 times or whatever, for the graph to be the graph of a function. So this is a function, it's got to pass the vertical line test, right? The y-axis should only pass through it once. So how could the tangent line be vertical there? Is the graph itself vertical? No, the graph is not vertical, but it looks more and more vertical as we zoom in. And let's use that manipulate feature now to zoom in. So I'm going to do manipulate. I'm going to put this plot inside here, like that. Put a comma and then an n square bracket. The little red caret here says, mathematics is saying, I want more input. What in the world am I trying to do? I haven't told you yet. What I'd like to do is I'd like to try to zoom in near the origin in this graph. How? Well, maybe we should use the Greek letter epsilon again, our old friend. Well, okay. To make the epsilon, I typed escape E escape. Makes an epsilon. Escape E escape. Escape E escape. Makes an epsilon. And I want that's going to be my x, the distance between, from the endpoints to the origin along the x-axis in my plotting window. I'd like that to go towards 0. Get really, really small here. And this is fine. It will make a plot like that. Oh, well, except I have to change the x's here. I have to change x instead of -8 to 8. How about negative epsilon to epsilon? Again, to make the epsilon do escape E escape. This will plot it. It will not keep the plot range in the y direction fixed, and so in that sense, it's not quite ideal. But let's see what it looks like anyway. Go ahead and enter this with the shift return. Should look like this, and I can see what epsilon is. I'm going to move the slider now to let epsilon go to 0. And yeah, because it's changing the y range as well, the graph doesn't look much different. What I'd like to do to make the graph look different as I zoom in is I'm going to do an extra thing, put another comma up here after the list containing the range of values for x. And let's do our old friend plot range with a capital P and a capital R. Arrow is again a negative sign, then a greater than sign. And then inside curly braces as a list, I'm going to type negative epsilon to epsilon. Again, make the epsilon with escape E escape. That'll zoom in a way that makes the graph look different as I zoom in. Watch what happens here. Zoom in, epsilon, make it smaller and smaller. Yeah, now the graph is looking different. And indeed, it is looking steeper and steeper at the origin. And in fact, if you go in far enough, it actually even looks practically vertical. If I want it even further, Add a couple zeros here. It looks so close to vertical, it looks like it's the y-axis. Is it the y-axis? No, it's actually not. It actually still passes the vertical line test. But it gets so close to being vertical that the tangent line itself actually is vertical. Kind of a weird thing to realize. But the main point of bringing this up, besides getting a little more practice with Mathematica, well, there's a few different points. One educational point is just to get more practice with the limit definition of a derivative. Another educational point is to emphasize the concept of differentiability and lack of differentiability. One way a function can fail to have a derivative is if the tangent line is vertical at a point. That's one way. There are other ways for a function to fail to be differentiable. Let's consider another example. Let's consider the example f of x equals the absolute value of x. The graph of this, I hope you remember from the past, it looks like a V, right? This equals x if x is greater than or equal to 0, and equals negative x if x is negative. But realize that when x is negative, negative x is positive, actually. That's very confusing for many people, but it is true. If x is negative, like, try an example, -5, what's the absolute value of -5? It's +5, which you could get by doing negative of -5. Two negatives make a positive. That's why some teachers often use the word opposite in this context. Opposite of x. Negative x, the opposite of x is not necessarily a negative number. It's positive, in fact, if x itself is negative. The graph over here is like the graph of y equals x. The graph over here is like the graph of y equals negative x. So the graph looks like a V. What's going to happen if we zoom in closer and closer to the origin in this graph? Let's just copy and paste this Mathematica code down here and change the cube root of x to the absolute value of x, which you can do as ABS, capital A, BS. The graph looks like a V. The scales are not the same, so it's kind of an elongated V. Here, if I let epsilon go towards 0 again, the graph does still pretty much have the same shape, and that is reality, actually. I don't need to modify, well, I did already modify this. It has the basic same shape, like a V. And at the origin, it never looks more and more like a line. It still looks like a tip of a V. Because of that, that means this function fails to be differentiable at the origin. Coming back to the formula, f prime of x in this context equals +1, slope of 1, if x is strictly positive, -1 if x is strictly negative, and is undefined, does not exist, dne, if x equals 0. I didn't really prove that. If I wanted to prove that f prime of 0 does not exist, I'd want to actually do the limit calculation and show that limit does not exist. Zero plus h is h, so I'm just writing an f of h there, not an f of 0 plus h. F of 0 itself is the absolute value of 0, which is 0. What's f of h? It's the absolute value of h. This limit was actually a homework problem from, I don't know, a week and a half ago or something. Remember this one? Does this limit exist or not? Well, graph this function. It was a function of x in the textbook problem, but now we're treating it as a function of h. this equals h over h, or 1 if h is positive, and equals the opposite of h over h, which is -1 if h is negative. And what does it equal if h equals 0? Trick question. Or you should know. Can you plug in h equals 0 there? No, you can't. It's undefined. Does not exist if h equals 0. The graph of this function is a horizontal line up at 1 when h is positive, and another horizontal line down at -1 when h is negative. But this function of h, which is what I'm graphing, is undefined when h equals 0, and that is a verification that f prime of 0 does not exist when x is 0 for this example. These are two different graphs, but they're related. This graph here is the graph to help me calculate this limit and see that it does not exist. The right-hand limit is +1, but the left-hand limit is -1, and those are not equal. So the two-sided limit does not exist. And again, that means f prime of 0 for this example, the absolute value function, does not exist. There's a corner in the graph. Never looks more like a straight line there. It's not differentiable at 0. F is differentiable everywhere except the x equals 0 again. Everywhere for all x except x equals 0. Let's try another example. How about f of x equals x to the 2/3 power? Does Mathematica treat it like a complex number? Let's see. Yeah. So instead, we need to take the cube root of, say, -8 and square that to really do a 2/3 power. And as far as a plot goes, I would need to square root the cube root of x function again. So I'm going to copy and paste this code down here and change the cube root of x to cube root of x squared. That's the same as x to the 2/3 power. I could also put the square inside the cube root. Either way is okay. There's the graph. Looks like we have an extra fancy looking corner there at the origin this time. As I zoom in toward the origin and wait for it to render more accurately, it's as I move, you can see near the origin it's inaccurate. But if I stop, it becomes more accurate. It never looks more and more like a line. In fact, it is a very sharp corner, you might say. Tip of a spear or something. So this function also fails to be differentiable at 0, which is maybe not so surprising, because if you use the power rule to find its derivative, you get 2/3 x to the 1/3, excuse me, -1/3. 2/3 minus 1 is -1/3, which is the same as 2/3 times the cube root of x. That's the cube root of x there. That's supposed to be a 3 there. Let me redo it. 2/3 times the cube root of x squared. Oh no, just cube root of x, excuse me. Which is definitely undefined which is defined everywhere except 0. So this is true as long as x is non-zero. Not surprising when you look at the graph. This function fails to be differentiable at 0. So that's the concept of differentiability. Another big thing to know about differentiability is when your function is differentiable, it will automatically be continuous. differentiable, meaning has a derivative, implies continuous. The graph does not have any breaks in it. That also means that if your function is not continuous at some point or over some interval, that will mean that it's also not differentiable. Because if it were differentiable, this fact would imply it's continuous. So another way to look for lack of differentiability is anytime you have a discontinuity. If you've got a discontinuity at a point, if your graph, say, looks like this, if that's the graph of f, then f prime of c does not exist because f is not continuous at c. So do you get the main points here? Differentiability means derivative exists. And I could talk about that at individual points. Is this function differentiable at this point or not? And I can talk about it over entire intervals. Is this function differentiable over this entire interval? Meaning, is it differentiable at every point? Lack of differentiability comes in essentially three flavors. Either you have a vertical tangent somewhere, like the cube root function, or you've got a corner in a graph, like the absolute value function, or, well, this sort of classifies as both. This is both a vertical tangent at the origin, but also it is a corner there. And again, there's some inaccuracies that go on unless I stop it. Okay? That's the idea of differentiability. That's the main topic of section 2.6. Section 2.6 is about differentiability. Let's go backwards now, though, and emphasize the geometric meaning of the first and second derivatives. I've mentioned that already, but let's re-emphasize it. Geometric interpretation of derivatives. This is really important. One, if f prime of x is strictly positive, say, for all x in some interval, I'm not going to say what the interval is, could be the entire real number line, could be some interval, like an open interval from 1 to 7 or something, containing all the numbers between 1 and 7, but not, say, the endpoints. The conclusion is then f is increasing on that interval. And some people would add the word strictly in there. In fact, I would usually add it, strictly increasing. If the derivative is always positive, the function is going up. On the other hand, if the derivative is always negative for all x in some interval, then f is strictly decreasing. On that interval. So your prototypical picture of a function whose derivative is always positive might be something like this. And if the derivative is always positive, that means the function's going up. It's increasing as x goes from left to right. Why? Well, intuitively, because the slope of the tangent's always positive. And the tangent line at any point is a really good approximation to the graph at that point. So at any point, I've got a positive slope tangent. The graph looks a lot like the tangent line near that point. And since that tangent line has a positive slope, that means the graph of f is going to be increasing. And here's a prototypical picture of a graph that's decreasing. This f prime is positive here, f prime is negative here. This is the graph of f I'm talking about, not the graph of f prime. But when the graph of f looks like this, and when the graph is smooth, is another word we use for differentiable. Differentiable means smooth. You'll hear that word used. F prime is positive, the graph of f is going up. If f prime of x is always negative, the graph is going down. If the f prime is both positive and negative on some interval, then the graph goes both up and down. Make sense? What about second derivatives? If f double prime of x, it's a double prime, let me rewrite it. F double prime of x is positive for all x in some interval. This adding for all x in some interval actually is very important. These facts actually become, well, not facts, they become false if you're only talking about isolated points. Like if f prime is positive at some number, like 0, if f prime of 0 is positive, that actually does not mean f is increasing near 0. I will show you examples of that probably on Wednesday or something, but not today. Then we can conclude that f is what's called concave up on that interval. Its graph looks like either an entire smile, or say part of a smile like this, or part of a smile like that. These are all different possibilities for the graph of f when f prime, double prime of x is positive. Why? Why are the graphs concave up? Why do they look like one of those three? Well, remember, f double prime of x is the derivative of the derivative. It's the derivative of f prime. So if f double prime is positive in some interval, that means the graph of f prime is increasing, not the graph of f, but the graph of f prime. And remember, we can graph f prime. So the graph, this means the graph of f prime, which I have not drawn here, the graph of f prime must be increasing. Well, what does that tell you about f? If the graph of f prime is going up, that means the slopes of f must be going up. You look at any one of these three graphs, slope of a tangent, the tangent lines increase as you move from left to right. Here the tangent line is negative, here it's close to 0, here the tangent line is positive. It's increasing as x increases. On this graph, the tangent line always has a negative slope, but it does get closer to 0. It is technically increasing. The negative number is going towards 0, it means it's getting larger technically on a number line. It's increasing. And here the slope is always positive and getting larger and larger. That's also concave up. And on the other hand, the flip side is if f double prime of x is negative for all x in some interval, then f is concave down. Concave down is what we call it on that interval. Looks like a full frown or part of a frown, one of those three. three different graphs of f where f double prime of x is always negative. F double prime is the derivative of f prime. When f double prime of x is negative for all x, that means f prime is decreasing. The graph of f prime, which I have not drawn here, would be going down, which means the slopes of f are decreasing. With this picture, they start out positive, but eventually become negative. With these two pictures, this one's always positive, but it is decreasing towards zero. This one, the slope is always negative and becoming more negative. So it is decreasing. Those purple lines are supposed to be tangent lines. Does that make sense? Can I clarify anything? Fundamental things to know from calculus right here. We'll do some examples here in a minute. Surprisingly, before I look at the examples, surprisingly, for each one of these statements, if I reverse the premises and the conclusions, if I form what's called the converse, you actually get a false statement, even though it sounds true. Try it with this one. If f is strictly increasing on some interval, and if f is differentiable at least on that interval, shouldn't f prime be always positive? If the graph of f is always going up, and f is differentiable, shouldn't its derivative always be positive? The answer is actually no. What? The graph's going up? Wouldn't all of its tangent lines have a positive slope? No, they don't. Here's an example where they don't. Instead of the cube root function, look at the cube function. F of x equals x cubed. This function is strictly increasing on any interval however, f prime of x equals 3x squared by the power rule, so f prime of 0 is 3 times 0 squared is 0, which is not positive. You know that? 0 is not positive. Positive means strictly greater than 0. 0 is not greater than itself. It's strictly increasing on any interval, but the derivative is 0 somewhere. Oh, that's so close to being true in the converse. Wouldn't it be true if I put a greater than or equal to sign there? Well, we'll think about that later. What's really going on here? The graph of x cubed looks about like this. It is always going up, but just as the cube root function had a vertical tangent at 0, the cubing function has a horizontal tangent at 0. It's never a horizontal graph. It is always increasing, but the tangent line at the origin looks more and more horizontal the closer you zoom in. Analogous to how that cube root function at the origin looked more and more vertical the closer we zoomed in. Some subtle things here, but definitely something to be aware of. All right, I'd like to use Mathematica more for the rest of the class here today. So you're going to have more problems thinking about graphs and second derivatives included. That will include thinking about graphical problems, like these say, and identifying, is the derivative positive or negative everywhere? And is the second derivative positive or negative everywhere? Or are they both 0, perhaps, like this one? more graphical interpretations. You're supposed to take these graphs and try to graph the second derivative. That's pretty tricky. I'll probably just assign one of those. What would I do? I would try to graph the first derivative first before you try to graph the second derivative. Problem doesn't ask for the graph of the first derivative, but if you're going to draw an accurate graph of the second derivative, you better try to graph the first derivative first. Do it like you did before. Try to estimate slopes of tangent lines first. Then draw f prime. And then once you got a good f prime, and you should be careful when you draw f prime, draw it nicely. You should try to draw little mini tangent lines to f prime to estimate f double prime. Well, in your final answer, you should be able to tell when you compare the graph of f with the graph of f double prime that f double prime is positive exactly where your original graph is concave up and negative where it's concave down. Like this graph right here. This one's concave down up until right around there when it becomes concave up until you get right about here where it becomes concave down again. So the graph of f double prime should be negative when x is between, well, off to negative infinity and up to maybe around -1 or so, where the concavity changes. It changes from a frown to a smile, or part of a smile. It's going to be positive in here, and then it become negative over here, where f is concave down. But yes, I would try to draw f prime first, then draw f double prime. So let's go back to Mathematica to end class today and try to re-emphasize these points. Let's go back to our example actually from last Friday. By the way, when you save these, it's probably a good idea to cut out your graphs. Just do a control cut or something like that, control X. Because if you leave your graphs in there, then the file size gets too big. And it's fine, just upload your code, that's fine. It doesn't have to include the graphs. By the way, I am behind on grading last Fridays. I didn't get that done. Question? It's like highlight your graph. Yeah, I highlighted the cell and then I did a control X, command X. Let's go back to that example from last Friday. F of t was t times t minus 1 times t minus 3. And in fact, let me reopen the one from last Friday just to save some time here. If I have it in my recents, hopefully. Yes. Actually, let's go ahead and graph the second derivative in here as well. You can type this if you want. F double prime of t. I'm adding that to the graph. So I copied and pasted, but you can go ahead and type this. Make sure you get the commas in the right spot, the curly braces in the right spot, the square brackets in the right spot. Capital letters where they belong. So now I'm graphing f, f prime, and f double prime. F was the cubic, that's the blue one. Its derivative is a quadratic, that's the goldish one, sort of yellowish orangish one. And f double prime is going to be linear. That's the straight line, the green line there. Think about it with me here. F prime of x, the orangish one, is positive when the blue one is increasing, like between 0 and 0.45 or so. See where my cursor is? That's where the graph of f prime is positive. And look at the graph of f, it's increasing until you reach a maximum approximately when x is 0.45. High point. Then f is decreasing, matching the fact that the f prime has a graph that's negative. The horizontal axis is right here. When the orangish graph is below the axis there, f prime is negative. The blue graph is decreasing. Then f prime becomes positive as x increases through about 2.21 or so, it looks like. That's when f prime changes from negative to positive, and therefore the graph of f changes from decreasing to increasing. Now think about f double prime, the green line. It's negative when x is less than about 1.32, I think it looks like. In other words, the blue graph is concave down when x is between 0 and about 1.32. There's a change in concavity right about at this point. That's where the frown ends. I mean, it's hard to tell it's a frown here because it looks pretty straight. Technically speaking, it's still concave down until you get to right about there. And past that point, f double prime is positive. Its graph is above the horizontal axis, and therefore the graph of f becomes concave up. These connections and being able to think about these things graphically, super important. Something I typically do test on for exam 2. It's also related to some big ideas in chapter 4, which we won't get to until after exam 2. Chapter 4 is all about, well, applications and optimization, or you might say applications of optimization. Trying to maximize or minimize a function. Listen carefully here. The blue graph, the graph of f, has what's called a local maximum near 0.45. It's, again, if you pretend that's a little hill, you're on the top of the hill there. It's a local maximum. That's not as high as you can get. It gets higher over here. But near this point, it's a maximum. F prime changes from positive to negative. The slope of the tangent lines change from having positive slope to having a negative slope. That's when you're going to have a little hill. On the other hand, the blue graph has a local minimum near x equals 2.21, right about there. F prime changes from negative to positive there. The slopes of tangent lines change from negative slopes to positive slopes. Really, really important to get this. This is all key concepts of differential calculus. Can I clarify anything there? It's best thought of with examples. Not only symbolic examples, but graphical examples like this. You should be practicing what I'm saying here numerous times in coming weeks. You should rethink about examples like this. Some people find them easy, some people find them hard, okay? It is a mixture. Something else I want to do in our last bit of time here is animate this. At least animate the graph of f, and if it represents a position, say, animate the actual motion. I'm trying to work toward the parametric equations that I keep telling you to read about in section 4.8, which is definitely ahead of where we are. I hope you did do some reading, at least about parametrizing lines and circles. I'm trying to get to that point. I don't know if I'll have time here in 8 minutes today. Remember, if this is a position, like of a bug traveling back and forth, like we talked about last Friday, you can imagine the bug traveling along the vertical axis here. How could I make an animation illustrating the motion? I could put this inside and manipulate, but I also would like to have a dot in here that goes up and down over time, representing the location of the bug. What I'm about to show you is kind of tricky. First of all, instead of doing a manipulate first, I'm going to put the word show here, and then a square bracket, and then put an end square bracket there. Then, right here, I'm going to put a comma. And I'm going to put, it's probably easiest to use what's called ListPlot, capital L, capital P. Notice how I put the starting square bracket and the ending square bracket there right away. That's to help me avoid the mistake of forgetting my end square bracket. And also reminding me with the little red caret that I need something inside the list plot. What am I going to put in here? Double curvy braces, and inside the double curvy braces, I'm going to put 0, comma f of b. But wait a minute, what's b? Hang on here. All of this I'm going to put inside manipulate. I'm going to type manipulate with a capital M, excuse me. Square bracket there and ending square bracket here. I see a little red up arrow telling me I want something in there. I need a comma there first though. So what I just typed is all this part, what I typed first. That is all inside the manipulate. And the B is going to be the value of time essentially. Maybe I should call it capital T. Change the B to a capital T. Capital T is going to be my animation parameter. It's going to start at 0 and go up to a little bit past 3, say 3.3. In fact, it is going to go up to this value here. I'm also going to change this to being a capital T so that my graph gets traced out over time. And actually, because of that, I'm going to change this number to being slightly bigger than 0, say 0.00001. What's this going to do? It's going to make not only the graph as capital T increases, but also a plot of a point on the y-axis whose coordinates are 0, f of t. To be on the y-axis means your first coordinate is 0. Its second coordinate is going to be whatever the value of f of t is. And got rid of my horizontal axis here. Okay. Let me do something to fix that though. Let me change the location of this n square bracket. I'm going to cut this one out and put it right here instead. And I'm also going to change my plot range like this. Okay, this is a spot where if you're not careful, you'll make a mistake and you'll get errors or nothing will plot. So I changed the location of the square bracket to being after the word automatic to instead being after the curly braces inside the plot there. And then I changed the plot range to look like this. If you forget a comma or put it double commas or put a square bracket in the wrong spot, it'll stay a mistake. But I think I did it right. Oh, I must have made a mistake myself. That's okay. Let's see. Fix my mistake. I can see this. There's probably a wrong square bracket somewhere or maybe an extra comma somewhere. Yeah, I think I know. I think I know what I need to do. Let me highlight this whole thing here and do a Command X. Or save it first if you're afraid that doing a Command X will delete it. It actually doesn't. The Command X will delete it, but it is stored, and I can now paste it over here. I think this will work. Yeah, it does. It's very likely you may have made a mistake, though, because I was making some mistakes. If you can't get it to work, don't worry about it. I will email you this file, or I'll put it on Moodle, and you can compare with what you have. What am I trying to do here? Again, the point is, I'm trying to model the motion. Now, because I put this in manipulate, it's going to make an animation for me as capital T increases. I can play this. And I see the graph, and I also see a little blue dot indicating the motion of the bug. Notice that I can slow this down to see it better. That the second coordinate of the bug on the y-axis is the same as the second coordinate of the point on the graph. Also note that it is keeping track of position and speed information. Now it's traveling relatively fast because this graph is relatively steep. The velocity is negative, but it's a large negative number. When this graph reaches a minimum, the bug is turning around and turning back the other way. Slower motion corresponds to slopes of this graph, the derivative being closer to zero. Faster motion, like right now, corresponds to a derivative that's high, either positively or low negatively. Far away from zero is when you have a very large speed. Okay. When we meet again on Wednesday, we will apply these ideas to motion in the plane, parametric equations, chapter 4.8. If you couldn't get this to work, if you got errors, don't worry about it. It's not a big deal. Just go ahead and save your PDF, this Mathematica file as a PDF. Go ahead and cut out the graphs. It's not a big deal. I just want to see the code there. Save it as a PDF, and that's going to be part of what you upload. And again, I'm not going to, if you got errors and couldn't fix it, it's okay. Okay? All right. Have a good day.